This is Mrs. Weinman, and this is a short video to explain how to draw free body diagrams. Free body diagrams are sometimes called force diagrams, and they're very useful tools in analyzing the forces acting on any situation. There are 3 simple steps. First one, you draw an object. It does not have to be a sophisticated piece of art. You can simply draw a point or a square. Identify the forces that are acting on your object, and then draw force vectors. All of these vectors will radiate from the center point of your object, and they will represent the different forces acting on an object. This is not a vector diagram, so we're not adding them tail to tail, but rather we're just indicating the directions that they're working in. Let's give it a try. In this situation, I have a girl who is at rest, but she is hanging from a rope. So we begin by drawing the girl, or in my case, I'm just going to draw a blob to represent the girl, and the rope. These are the 2 objects in my system. Let's identify the forces. Well, we're interested in the forces acting on the girl. So first of all, the girl's weight. The girl's weight is due to gravity, so it is a vector pointing down. The next is the supporting force, which is provided by the rope, the tension in the rope. Now, since she's not going up and she's not going down, that vector that represents the tension is going to be equal in magnitude and opposite in direction. Let's look at another slightly more complex situation. In this case, we are pushing a box across the table. So again, we begin by identifying the forces. We have the weight of the box. It is still on the earth, so the weight arrow points towards the center of the earth. But our box isn't falling towards the center of the earth. It too has a supporting force. We can't see a rope, but that supporting force is being provided by the table. We refer to that supporting force as the normal force. A normal force is any supporting force, and it is always drawn perpendicular to the surface. In this case, our normal force is provided by the table. We're pushing it forward, so we draw an arrow radiating from a point in the center in the forward direction. Notice our push is actually coming from the other side of the block, but that doesn't matter. We draw the force in the direction it is being exerted. If there's friction on this table, we are going to draw a 4th force, and that would represent the force of friction. Notice that it is backwards. Friction is a force that always opposes motion, and so it is backwards of the motion of the box. It also is not as strong as the forward push. So I've indicated that by drawing a force vector for friction that is slightly shorter than the force vector for the push. What do we do if our box is on a table that has been tilted? Well, the rules don't change. We begin by drawing the weight. And which way does the weight work? Towards the center of the earth. The table is still providing a supporting force. It's not quite enough to keep it from slipping down, but it's still supporting it some. And so in this case, the normal force is drawn, as the rule says, perpendicular to the surface, so it is drawn upwards. If there's friction on this table, it is drawn in the direction opposite of motion. There it is, force of friction. Again, it's not great. We actually don't know how long it is, but we know it's going to be smaller if it's going on down the hill. And we are actually done with this force diagram. That's all the forces acting on it. Now you might wonder, well, it's going down the hill. Shouldn't there be a downhill force? Well, there's no new force providing that downhill. There's no finger pushing on our box this time. The downhill component of the force is provided by the weight. Later on, we'll resolve that weight into its components that make it up. But right now, it's not a separate force. It's incorporated in that weight vector. So here's a few tips in general. Free body diagrams are not sketches. They follow rules. Be careful when you draw them. Consider your system. Sometimes it's tempting to draw the forces acting on the object and the forces the object is exerting on something else, but don't. Just think of the one object. What forces are acting on that object? Draw all the force vectors radiating from a point at the center of mass of the object. The length should indicate how big the force is, the magnitude of the force. And finally, always draw your weight towards this, working towards the center of the Earth, regardless of whether your object is twisted or on a tilted or whatever's happening to it. Weight always works towards the center of the Earth. Happy drawing!